Welcome back to Calculus. We're going to be talking about functions today. A function is basically a relation in which every input has exactly one output. That's a pretty important definition. And function notation is basically usually it's f of x, where x is the input, f is the name of the function. Sometimes it's also g of x, sometimes k of x. It really depends on the context. And when you're talking about polynomials in specific, you're talking about p of x or q of x. Those both are general names for polynomials. So, how do you do stuff with functions? That's basically what we're going to talk about today. First of all, you can graph them. And we'll be talking about linear functions first and foremost, also called as lines. So, if I were to draw a coordinate axes like this, and I want to graph a line, most lines or linear functions would be expressed in the form y is equal to mx plus b. This is called slope-intercept form, where m is the slope and b is the y-intercept. Now, slope is a very important theme in calculus. In fact, it drives one of the main aspects of calculus. But slope of a linear function we learn all the way back in Algebra 1 when we learn to graph lines. So when you're given the slope and the y-intercept, you can easily graph a line. Moving on, there's one more thing we need to talk about with lines. When you're given the equation of a line, especially in slope-intercept form, it's easiest in that form, you can find the slope of the parallel and perpendicular lines to that line. What am I talking about? Well, a parallel line basically never intersects the first line. So these two are parallel. No matter how long you extend them, they'll never intersect. A perpendicular line intersects it at a 90-degree angle. So how do you find the slope of a parallel and perpendicular line? Given this, the slope of the parallel line will just be the same as the slope of the normal line, because it's just the same rate of change, because slope is rate of change, so it never intersects each other. But for perpendicular lines, so this is for parallel, let me just abbreviate that. For perpendicular lines, it's a bit more complex formula. It would be negative 1 over m. So you basically take the negative of the reciprocal of the slope. So if I had a slope like 2/3, the parallel line would also be 2/3, and the perpendicular line would be negative 3 over 2. I'm taking the reciprocal of it, and I'm taking the negative of that. So that's basically what you can do with lines. General functions, you can actually do quite a lot. So for polynomial functions, there are two main categories other than lines. We just talked about lines, so I'm ignoring that for now. There's even functions and odd functions. These apply to all functions. Actually, like any function can be classified as even, odd, or neither. But when you're talking about polynomials specifically, it's talking about their degree. Even functions have an even degree, and odd functions have an odd degree, as expected. When you have even degree, you would mostly see something that looks like this or like this. When you get to more complex polynomials that have multiple terms, it'll look a lot like this. And this is how a more complicated polynomial graph would look like. And graphing polynomials is all covered in pre-calculus. But odd polynomials, that's a completely different thing. They generally have something that looks like this, and more complicated ones can look much more different like that. You know, just normal stuff. Rational functions also look interesting. They mostly look like hyperbolas, like this. And if you know conic seconds, you know what I'm talking about. Parabolas, hyperbolas, circles, and ellipses. A hyperbola looks something like this. But there are also graphs of 1 over x squared, for example. This is 1 over x squared, so it doesn't really look like a hyperbola that much, but same general shape on each side. Now, there are a few more topics about functions that we need to know. First of all, how to determine a function. When you're given the graph of a function, there's something called the vertical line test. So let's say this is a function. The vertical line test, basically you draw vertical lines at any point on the function, and if they always intersect at exactly one point on the function, that means it's a function. So this is basically echoing the definition of a function, which states that every input has exactly one output. The vertical lines are the input because they have exactly one x value. Now the points they intersect are the output because that's where the function actually is. If there's exactly one output, that means it's a function. And there's a similar test like the vertical line test called the horizontal line test. And this one's a bit different, and it's for testing for one-to-one. One-to-one basically means that for every input, there's exactly one output, and for every output, there's exactly one input. So something like this, a line basically, is one-to-one. But a more complicated polynomial like this is not one-to-one because it does not pass the horizontal line test. It passes it for a few points, but not all of them. Inverse functions are also important. If you have f of x as some function, then the inverse function of it is represented by a little negative one up there. That's not an exponent. Some people might think it's an exponent, but it just means inverse. So inverse of the function, you can calculate it by switching x and y in the function and then solving for y again. And that's a pretty complicated process. A quick example would be a line, y is equal to 2x plus 3. You would switch x and y, you get x is equal to 2y plus 3. Then you solve for y, you subtract 3 from both sides, and then you divide that by 2. You get y is equal to subtract 3, you get x minus 3, then divide by 2, you get x minus 3 over 2, and that would be the equation for your inverse function. You'd also have to check that the inverse function is actually a function. That's why one-to-one is so necessary, because when you're inverting it, it might not be a function if the original function wasn't one-to-one. Okay, the last thing we need to talk about in regard to functions is composition of functions and transformations with functions. When you have two functions, you can compose them together. For example, f of x and g of x. The composition would basically be putting one function as the other function's input. So f of g of x. And note that this is not always going to be equal to g of f of x. They can be different. In rare cases, they're the same, but usually they're different. And transformations of functions. So when you're given a function f of x, there are a multitude of transformations we can do. We can basically translate it or move it. So if I had a function like this and I wanted to move it upwards, I can do that. Well, that's technically like an animation that I'm doing, but like on an actual graph, we can move it upwards, and that's like adding a constant to the end of the function. It's usually called k. And you can also move it downwards, and that'll just make the constant negative because you're moving it downwards. You can move it horizontally. If you're moving it horizontally to the right, it becomes f of x minus h. So in this case, it's a negative thing over here. So if it's like x minus 2, that means it's moving it to the right. It seems a bit contradictory, but it would be that formula. And then if you're moving it to the left, as you would assume, h would be negative, so it'll become x plus some value, like x plus 2, because h is negative. H is equal to negative 2 here, so negative of a negative becomes x plus 2. You can also stretch and shrink functions. This is like a horizontal shrink or horizontal compression, and it's similar to a vertical stretch in this case because you're doing the same thing. Since I'm expanding it out horizontally, I'm shrinking it vertically. So those are two different things you can do. In a horizontal shrink or stretch, you would put the constant right in here with the input. It'll be something like f of b times x. And in a vertical stretch or shrink, it'll be outside, like a times f of x. That's basically a crash course on most of the topics you need to know about functions. We'll be going more in depth into specific types of functions, such as trigonometric, exponential, and logarithmic functions in the future videos. And that's all you need to know about functions today. So I'll see you in the next video.